Hello. New topic. So this is, the first part of the course has really had to do a lot with signals and basic things to do with signals like convolution and extensions of kinds of signals like distributions. Today, we'll start talking about genuinely kind of new topic, and that's Fourier transform theory. So this is, another one of those major subjects in mathematics that you touch upon when learning this branch of applications of mathematics. And one can dig into it quite a lot more deeply than we are here, but we'll try to get a basic feel for some of the important issues that arise in the theory of Fourier transforms. So a warning about terminology. When you say Fourier transform, typically that means a very specific thing. And I'm not going to use that kind of terminology in this course. So when I say Fourier transform, I'm either talking in abstraction and generality, like I am now, or I will have to tell you which of the four possible Fourier transforms that we're going to talk about, I'm talking about at that time. And so this is not common terminology. So my use of the word Fourier transform with adjectives in front of it, we're going to talk about, as I said, four flavors of Fourier transforms. That's not normal. So be aware of that. Okay, the idea of Fourier transform theory, and we talked about this in the initial sort of preparatory lecture. The idea of Fourier transform theory is that we take a function of time So, we're now used to these things. And then you apply a Fourier transform to it. And what you get back is you get a function of frequency, which for the moment I'll write as omega, but that's not how we're going to represent it when we come to actually doing this. Okay. And so, so the idea is in here, you have at each time you specify a value of the function, and then over here you take a transform, and then rather than as a function of time, you have something which is a function of frequency. And the idea is that at a prescribed frequency, this tells you sort of the content of the of your time signal at that frequency. Okay, now that's very vague, and so let's try to be specific. So the breakdown of the four kinds of Fourier transforms we're going to talk about will come into two classes of two. So we'll talk about continuous and discrete time. Okay, that's two options, and we'll also talk about periodic and aperiodic, basically just meaning not periodic. So to motivate things, the easiest place to start is with periodic continuous time. All right, and so this discussion is going to be very informal. We'll do real things starting next time, but this is just to kind of get the ball rolling and get some initial ideas under our belt about what it is that we're talking about. So let's think about the continuous time. periodic case. Okay. All right, so we have f is some, and so it's continuous time. And when talking about Fourier transform theory, it's easiest actually to talk about complex signals. And so we're going to switch from thinking about f being r or c to being signals taking values in the complex numbers, and we'll see the reasons why that is. Okay, so we have some t periodic signal f. Okay, now what might it mean to say what is the content of f at some frequency? Now, one of the reasons why the continuous time periodic case is the easiest to motivate is that it comes equipped with a bunch of natural frequencies, which are namely the integer multiples of 1 over the period, right? So 1 over period is frequency. And so we will represent f as a sum of harmonics at frequencies that are integer multiples of the natural frequency that comes with the t periodicity. Okay. So the harmonics are well, the complex harmonics look like this: e to the 2 pi I t over t. Sorry, my n. 2 pi I n t over t. Okay, so remember that this is cosine 2 pi n t over t plus I sine 2 pi n t over t. Okay. So these are the complex version of the harmonics, and you can also represent things in terms of the real harmonics, and these are just the sines and the cosines themselves. Now you can do it in either. You can either use this or you can use these. And this is one of the reasons why in Fourier analysis it's easier to use the complex signals, because it's just easier to talk about the complex harmonics rather than to have to kind of deal separately with sines and cosines. Okay, because there's sort of separate formulas that are little niggly things you have to deal with, like for example, when n is equal to 0, the cosine function is 1 and the sine function is 0. So you always have to bookkeep the fact that the cosine makes sense or has a contribution at n equals 0, but the sine does not. And there's all these other things that you have to deal with, and it's just easier to work with the complex harmonics. But you can convert all the formulas. And when we talk about the transforms, I'll sort of give the formulas, or at least for one of the transforms, I'll give the formulas for the sort of sine and cosine version, but we're almost always going to work with the complex harmonic version. Okay. There's just an elegance doing things that way, which makes it much easier to present the theory using complex harmonics, even if you decide you're going to, in practice, work with sines and cosines. Okay, so and I'm not going to put an equals sign here because that doesn't quite make sense. Okay, so the idea is you want to write, as I say, F is a linear combination of these harmonic signals. Okay, so it's very much not clear that that's a reasonable thing to do, and the reasonableness of that exactly comes down to what that little tilde symbol might mean. But that has to do with things like convergence of this infinite series, and those are things that we're going to talk about. Okay, but let's just forget about the finicky mathematics for a moment, and just pretend like this formula actually makes sense, and try to deduce what these coefficients in the linear combination must be. Okay. So what we're going to do is we're going to take this kind of meaningless formula, and we're going to do some therefore meaningless calculations with it. And what I'll do is I'm going to take both sides of this meaningless formula and multiply it by one of the harmonics. Okay. Right. And so I'm going to go, therefore, f of t, okay? And what I'll do is I'm going to multiply it by the harmonic e to the 2 minus 2 pi I m t over t dt, and then I'm going to integrate over a period. Okay. And then I'll do the same thing here. And because I'm, sort of in fantasy land where I get to do whatever I want, I can take this product and move it inside the infinite sum, whose convergence I know nothing about. Okay, and similarly, you can swap the integral with the sum, and you get sum n z c n e to the 2 pi I, and then it's n minus m t over t. All right. Okay, so now, oh, sorry, and I forgot the integral here. Integral, oops, integral from 0 to t dt. Okay. All right, so now you notice that when n is not equal to m, then I do this integral, and you just calculate the integral, and you use periodicity of the complex harmonics to see that at the endpoints you're going to get the same thing. That's what periodicity means, and so when n is not equal to m, then this thing is equal to 0. Okay. Now, when n is equal to m, then that's 0, and then the harmonic here that you're talking about is just the signal 1, and so then you're just integrating 1 from 0 to t, which is a pretty easy integral to do. It's t, right? So what you get here is you get 0 when n is not equal to m, and you get t c m, okay, when n is equal to m. All right. And so therefore, this tells you, okay, that Cm is equal to 1 over t, integral from 0 to t, f of t, e to the minus 2 pi I m t over t dt. Okay. Now, you can ask yourself now why it is that I chose to multiply here by, why did I put the minus sign there? I seem to have known what I was doing before I started, because I knew that it would give me the right conclusion here. And so one reason that I did this is because it works. And there's another reason why you do it that way, and that has to do with inner products. But we're going to talk about that carefully later on. Right now, we're just kind of doing motivational and kind of meaningless calculation. Okay. And so this tells you that the coefficients in this linear combination are calculated in this way. Okay, and as I say, you can think of this integral as being an inner product of f with the harmonic. All right, but that aside, if you sort of accept that this kind of senseless formula has some justification to it, this does tell you what the coefficients kind of should be in order for a sum like this to work out. All right. Okay, and so based on that, we're going to define the first of our Fourier transforms. Okay, and so what does this thing do? Okay, so it's going to take, and I'm going to call this FCD. Okay, and the reason that I'm going to do that is the C here means continuous and the D means discrete. Okay, so C means continuous time, and D means discrete frequency. Okay, because discrete frequency, because I've chosen this collection of discrete frequencies. All right, and so this is going to take an F. Okay, and then it's going to evaluate it. So first, let me maybe write this as with a proper domain and a codomain. Okay, so where should F live in order for me to be able to calculate this? Well, we'll do this slightly more carefully down the road, but in order for this integrand to be integrable over 0t, it's necessary and sufficient that its absolute value be integrable. This is one of the things we learned from Lebesgue integration, is that a function's integrable if and only if its absolute value is integrable. So we're going to take the absolute value of this, which is the product of the absolute value of those, but the absolute value of this is 1, and so this just means that the integral of the absolute value of f should exist, and that just means that f should be in L1 over 0t. So the domain here of the CDFT is L1 per. Okay, so T-periodic signals that are over each period are in L1. Okay. Now, what do I get out of this? Well, what I get out of this is I get some discrete frequency function defined on this discrete frequency domain with sample interval 1 over t. Okay, so I get something which takes values in C on the sampled frequency domain with sampling interval of 1 over t. Okay, so this just means that at each integer multiple of 1 over t, I assign a complex number, and the complex number is just that, and I'm not going to actually include the 1 over t in the definition. All right, so it's going to be f maps to integral from 0 to t, f of t. So sorry, let me write it like this. Okay, so this is going to be a function of frequency, and the frequencies are going to be of the form n over t. Okay, and it's going to map that frequency n over t into the thing that I was just about to write. Okay, and so this means that it takes this function into this function, right? So this function is a function of this discrete frequency variable. Okay, so in other words, f c d of f of n over t is integral from 0 to t f of t e to the minus 2 pi t over t dt. Okay, so that's our first Fourier transform. Okay, so it takes a continuous periodic f and returns a discrete aperiodic transformed function. Right? Okay. Oh yeah, so I was, you might sort of be concerned about the absence of the 1 over t here. It doesn't matter, it's just a scalar. We can kind of define this however we want. And it turns out that there's a bunch of rules about how, if you write these transforms in their inverses, which we'll talk about in the right way, then all the formulas are really nice. And one of the rules is this 1 over t doesn't show up here, it shows up somewhere else. It shows up in the inverse, but we'll talk about that when we get to it. Okay, good. So that's our first transform. And that one we kind of justified a little bit carefully in the sense that we wrote down a bogus formula and then we did some bogus calculations with it, but at least there was something that we could get our hands on. For the next transform, it's going to be just by analogy, which is a pretty weak way to motivate something, but that's what we're going to do. Okay, and so this will correspond to the continuous time aperiodic case. Okay. All right, now in the periodic case, we had a natural frequency to work with. In the aperiodic case, so these are going to be functions defined on all of R again, but they're not going to have any natural period. And so there's no natural frequency that you can, sort of use as a crutch to define, a function that looks like, or a relationship that looks like that. Okay. So as I say, what we're going to do instead is we're going to just take the formula here, and we're going to argue by feeble analogy. So the first thing when you try to adapt this formula is you first have to not stick to harmonics of this particular frequency, which are frequencies which are integer multiples of 1 over t. Okay. And so f from R to C is aperiodic. It has to be more than that, but let's not get into the technicalities right now. It's the transform will be a function of all frequencies, not just a discrete collection of frequencies. Okay, and so what that means really is it means replacing n over t in this formula with an arbitrary real number. So we replace the discrete frequencies n over t with continuous frequency. Okay, just like continuous time, okay, I have continuous frequency. And we denote this frequency by nu. Okay, so that's the variable that we're going to use as our frequency variable, right? So this is, my picture that I drew up here. I used omega, but that's not what we're going to use. We're going to use nu. Okay. And so, okay, so that's one adaptation of this formula. So we're going to replace n over t with nu. And of course, our signals are no longer periodic. And so this means that the integrals won't be over 0 to t. They'll be over r. Okay. Right. And so therefore, we're going to think of the transform as a function of frequency. It's going to be the integral over r f of t e to the minus 2 pi I nu t dt. Okay. Right. And so again, the way that I'm asking you to swallow this is by analogy. Okay, so I have this formula, which we can kind of justify in some way. And then I'm going to do some adaptations to this formula to motivate how we talk about aperiodic signals. Okay, so the frequency variable and the integral are adapted from here, but using the fact that we don't have any natural frequency, 1 over t in this case. Okay, and so we need now to sort of make this a little bit official, so we need for this integrand to be integrable, and the same arguments apply, right? So the modulus of this is 1, and so a necessary and sufficient condition for this integral to exist is that f be in L1. Okay, and so we get FCC, okay, of f. Sorry, FCC is going to be a mapping from L1, and we don't really know that much about the as a function of nu. Okay, so this thing now is going to be a function of nu. We don't know very much about what kind of function of nu it is. It turns out it'll be it'll have some particularly nice properties. It'll be continuous, for example. And we didn't here either. It's just that in the discrete time case, this isn't so horrible a thing to think about, but in the real case, it is. Sorry, but in the continuous time case, this isn't so pleasant. C to the r is not such a useful thing, but nonetheless, that's all we're going to be able to say right now. Okay, so this is just going to be some c-valued function on r. okay, some function of nu. And it's going to take an f in L1, and it's going to map it to this function of the frequency variable nu. Okay. So in other words, I get FCC, okay, and this is FCC, so it'll always be the case that C means continuous and D means discrete, so this means continuous time, continuous frequency, okay, because that's what I have here, continuous time, continuous frequency. Like so, okay? So those are my two continuous time Fourier transforms, okay? Now let's talk about the discrete versions of those transforms, okay? All right, so first let's talk about the discrete time. Aperiodic case. All right, so I have now F is discrete time, so it's going to be defined on some sampled interval Z of delta into the complex numbers. And again, I will now argue by analogy, and the analogy that I'm going to use here is this one. Okay, so I built this on a shaky analogy already, so now I'm going to build shakily on that shaky analogy to sort of see how we're going to write the Fourier transform of a signal like this. Okay, and the analogy here is simple. Time now is going to be sampled time. Okay, frequency is still going to be a continuous frequency. All right, and the integral is going to be replaced with a sum because the integral is over R, which is over time, and here time is discrete, so the integral is going to be a sum. Okay, so by analogy, okay, we use continuous frequency and we sum over our discrete times. Okay, and so the point is that we get a function of the continuous frequency variable, nu, okay, and it's going to be at a frequency nu, we're going to sum over k in the integers, right? So it's going to be f of, right, t, but t is going to be integer multiples of delta. All right, and then it's going to be e to the minus 2 pi I nu, all right, but t now is k delta, and so I get a formula like that. Okay, and so you see here that you get these are periodic harmonics. Okay, and what are the periods of these? Okay, so these are now functions of nu. Okay, and the period of this is 1 over delta. Right? So these harmonics are the same kinds of things as I had in my CDFT, except, I had t instead of nu, and I had 1 over capital T instead of delta. Other than that, it's the same kind of function. So they're periodic harmonics, but now they're functions of frequency. Okay, so this thing is a continuous time. Well, continuous frequency harmonic of period 1 over delta. Okay, so the roles of capital T in the T periodic case and the sampling interval delta get swapped here. All right, so again, let's make this kind of semi-official. Okay, and write a transform with a proper domain and a codomain that I'm not going to be able to say very much about at this point. Right, and so I need now for this sum to exist, and the argument for the existence of the sum is rather like the argument for the existence of the integrals above. So I'm going to ask for absolute convergence of this sum, and again that has magnitude 1, and so what you end up with is that f has to be in little l1. Okay, so we get this new transform f dc. Okay, so this is going to be from little l1 of z delta into c, and what are we going to get back? We're going to get back a continuous frequency function, but I don't really know very much about how this thing depends on nu, right? It turns out if f is in little l1, turns out this thing is going to be a continuous periodic function, but that's jumping ahead of ourselves. All we know now really is that this is a complex valued function on the real line. It should be periodic with period 1 over delta, just because each of the terms in the sum here is, but at this point, this is all I'm going to write. Okay. And so this takes an f, which is in little l1, and it maps it to this function of frequency. Okay. All right. All right, so that's our discrete time continuous frequency transform, FDC. Okay, so in other words, FDC of f of nu is so sorry here. I have these rules about how I write down formulas for transforms, and one of the rules is, so this is the first time we've had a discrete transform, and so there's a summation, and one of the rules is that whenever you have a sum, we're going to put the sample interval out front of the sum. And the sample interval here is delta. Okay. Right, so this is we're summing over the sampled time interval z of delta, and so sums in Fourier theory should always have a delta in front of them, and the reasons that we'll see. Right, so we're just going to stick to that convention regardless. Right, and so delta appears here too. It's a constant, and it'll show up one way or the other, and where you locate it can cause you pain, or it can cause you great joy. And we'll go with the second one. Okay. All right, so that's our third Fourier transform. And so then the final Fourier transform is the discrete time, discrete frequency. Okay, so we're going to get, these are going to be discrete time, periodic signals. Okay. All right, so F now is going to be, again, discrete time. So it's going to be defined on the sampled interval, the sampling interval delta, taking values in C, but it's going to be T periodic. Right, and so this means if a sampled, a discrete time signal has a period T, T must necessarily therefore be some multiple of delta, say capital N times delta. All right, so the roles of T and N are the same here. They define the period. All right. Okay, and again, we're going to work by analogy. All right. So what you're going to get here, oops. So what you're going to get here is you're going to get the same, you're going to get a sum because we're working with discrete time, but now frequencies are going to be discrete. Okay, so nu isn't going to be a continuous frequency variable. We're going to replace nu with a discrete frequency variable. And what will that discrete frequency variable be? What it's going to be is, again, by analogy. Okay, and the analogy here we're going to use is we're going to go back up to the first transform we talked about. And what was the discrete frequency that we used here? Well, the discrete frequency were the integer multiples of the period, the frequency, which is 1 over the period. Okay, and so we're going to do the same thing for in the discrete time, discrete frequency case. Okay, so the transformed function of frequency will be, okay, first of all, it's going to be discrete frequency. And this is because F is periodic. And it's going to be periodic. And this is because F is discrete time. Okay. All right, so it's discrete frequency. So the sample interval in the frequency domain is integer multiples of the period, okay, which is integer multiples of n delta. Okay, yeah, so the period is n delta. Okay, so that's what the sampling interval is going to be. All right, and the period in the frequency domain okay, and here we look at the formula here, okay, and we see that the these are periodic, with period being integer multiples of 1 over delta. Okay, so the period in the frequency domain is 1 over delta. Okay, so it's discrete frequency signals with this. Sorry, I didn't mean to have the N there. Okay, so they're discrete frequency variables with this discrete frequency signals with this sampling interval, and they're periodic with this period. Okay. All right. And so the transform is going to be now FDD. Okay. So a discrete time, discrete frequency of F of, okay. So it's going to be, again, discrete frequency with this sample interval. Okay, so that'll be N over N delta. Okay. And then I'm going to have now a formula for it. Okay, and so I'm going to combine. Sorry, I'm going to combine this formula, which is involves summations, with this formula, which involves periodicity. And so I'm going to get a sum now over one of the periods. Okay. And so let's say that sum is k equals 0 to n minus 1. Okay. And so it doesn't matter which period you use, but that's the one that we're going to use. So it's f of k delta. All right, and let's take a look at what the 2 pi I. Okay, so what we're going to get is we're going to get this thing. Okay, but new here is going to be the discrete frequency variable, which is going to be multiples of 1 over delta. So in other words, new is going to be k delta. All right, and so the deltas are going to cancel out. And so I'm going to get 2 pi I. So it's going to be k. Right, so sorry, new is going to be, right, I apologize. New is going to be integer multiples of this thing. Okay, so new is going to be replaced by n delta, little n delta over n delta. Okay, and k delta is k delta. Okay, so the point is, what I get is I get the k n over n, right? Because the deltas cancel is the point. All right. All right, so there's my my fourth Fourier transform, the discrete Fourier transform. And the only other thing I need to bookkeep here is I need to bookkeep the fact that whenever I have a sum in Fourier theory, I'm going to put the sample interval out front. All right. Okay. And so notice that FDD is a mapping from where to where? Well, it's going to be discrete time periodic, so that's L per, with sampling interval delta, into, again, discrete frequency with periodic, with sample interval 1 over n delta, Okay, and both of these spaces are finite dimensional, right? So discrete time periodic and discrete frequency periodic, those things are going to be um, um, finite dimensional, as we've talked about before. So there's no ones or anything you have to play around with here. These are just finite dimensional spaces. Okay, so this is just a finite dimensional linear map, and you can represent it by a matrix if you choose bases for these things, and you can choose bases based on these harmonics. Okay, all right, so those are our four transforms, all right? Now, what do we want to do? Now we want to invert these transforms. Okay, so in other words, if I give you we want a formula and I'll say a means of recovering f from the Fourier transform of f. Okay, and this could mean any one of our four Fourier transforms, and f could be any one of our four kinds of signals. Okay, and so there's immediately already, in the case of the CDFT, our justification for how we define this thing already gives us the inverse, right? And the justification is from that formula, okay? Because we know now that these CNs, okay, these are just except for the factor of 1 over t, these are just the values of the CDFT of f evaluated at the discrete frequencies n over t, okay? And so you can just say that to recover f, you just plug in the CNs, okay, which are, you know, this whole business is just FCD of FCD of f at n over t, okay? And so in that way, you recover f from its CDFT just directly from the way that we define, or the way that we motivated the definition of the transform in that case, okay? All right, so for the CDFT, okay, our motivation for the definition of FCD immediately suggests seeking an inverse of the form. Okay, and so F CD, and I'm going to write this as FCD inverse. Just, you know, again, since we're not really being careful about anything here, we can write anything we want. And so let me put here a capital F. Okay, so F is going to be some function of frequency, and so in this case, it's the discrete frequency with sampling interval 1 over t. And so FCD of f of t, okay, is going to be sum, okay, n in the integers, f of n over t, okay, e to the 2 pi I n t over t, okay, and so this, just to clarify, that formula is coming from here. Okay, so in other words, what I'm doing is I'm taking capital F to be the thing which at n over t is that. Okay, but there's this little factor of 1 over t that I have to take care of, but that gets taken care of automatically here because, as I've said in Fourier theory, whenever I have a sum, like I do here, I put the sampling interval out front. And so there's my 1 over t. So it kind of shows up automatically by my rules, right? So indeed, just to kind of close the loop on this discussion, our justification for the definition of FCD was that FCD inverse of FCD of F was equal to F, right? Okay, so in other words, F of T, this was our formula that we wrote down. Again, none of these equal signs are actually reasonable, but let's not fuss with it. Okay. F of T is 1 over T, sum n integers F C D of F over n over T e to the 2 pi over T, okay? So that's the CDFT. So our inverse looks like this. Okay, now what we're going to do for the other cases is we're going to do like we did for the definition of the forward transform, and that is we're just going to proceed by analogy. Okay. So analogously, for the for FCC, we have FCC inverse of, so again, I'll take some function of frequency, capital F, okay? And the analog here is going to be the analog of this formula, okay? But the analog of this formula is I replace the sum with an integral, okay? And I replace the discrete frequency variable with a continuous frequency variable, and I kind of close my eyes and erase the 1 over t. Okay, so the integral here is now over the continuous frequency variable nu. Okay. All right. So there's the, a guess at the inverse for the CCFT. For the DCFT. Okay, so remember that capital F here now is going to be a periodic continuous time function of frequency. Okay, and what we get back is we get a aperiodic discrete time function evaluated at integer multiples of k delta, right? And so the formula that we're going to get here, okay, is I have this formula that defines the forward transform, okay? Now, how are you going to recover F from this formula? Well, you're going to do exactly the same calculation as I did up here, right? So I started with a formula which is exactly like this one, okay, except the roles of and of time and frequency are reversed, okay? But I'm going to multiply it by a harmonic here, do the integral from 0 to t, but t in this case is 1 over delta, all right? And what I get is I get that the inverse of the dCFT should look like this. Should be the integral from 0 to the period, which is 1 over delta, okay, f of nu, okay, because f is now the frequency function, which is a function of a continuous frequency variable. That's e to the 2 pi I nu k delta d nu. Okay, so the thing you notice here is that the inverse of the dCFT looks rather like the forward transform for the CCFT. Okay, again, with the roles of time and frequency reversed, and that the inverse of the the CDFT, okay, which is that, okay, looks rather like the forward transform for the DCFT. Okay, so there's some symmetry that happens there. It's not perfect. You have to be careful in understanding that. It's perfect in some cases, but certainly the formulas are very suggestive. Okay, and then finally, you have the inverse of the DDFT, okay? And again, this is going to be evaluated on the sampled time interval with sampling interval delta. And you're going to get a sum here. And it's going to be k equals 0 to n minus 1 again, okay? Now it's going to be f, okay? And remember what the sample interval here is for the DDFT, okay? So the sample interval was 1 over n delta. So it's going to be k over n delta, okay? And that's going to be e to the 2 pi I, all right? So we're going to get a formula that's rather similar to this one, except the continuous frequency variable now, nu, is going to be replaced with, oh, sorry. This should be, apologize. This one should be n, oops, n and n, okay? Except nu is going to be replaced with n, or little n over n delta, and so deltas are going to cancel out just like they did before, and so I'm going to get here. Let me try to write it in a way that is as compatible as possible. Okay, 2 pi I n k over n. Okay. All right, and so in this case, you see that the forward, that the forward and inverse transforms for the DDFT look the same as one another. Okay, here. Okay, and then the only thing I have to kludge, because I need to do this, well, you don't need to, but just like I said, everything works out if you do this. And we won't, the payoff here won't come until sometime in the future, but we're going to follow the policy just without any thought of just putting, every time you see a sum in Fourier theory, you put the sampling interval out front. Okay. All right, so those are our 4 Fourier transforms and their inverses. Okay, so these are the formulas that we're going to work with, and there's lots of stuff we need to do to try to make sense of those formulas, and we're going to see that they don't always make sense, and so you need to come up with conditions on f so that they do make sense, and things like this. So there's lots of hard work to do to get somewhere here. Excuse me. So what are the things we're going to address? All right, so for the forward transform, what properties of f are revealed in the Fourier transform of f? Okay, so in other words, are there things about f that you can tell without actually knowing anything about f, but just by looking at its transform? Okay, and this is a useful thing. Because sometimes when you collect data, the data that you collect, or certainly the most meaningful form of the data that you collect, comes not as the signals coming to you as a function of time, but by looking at the spectrum of the signals. So which really just amounts to looking at the Fourier transform. Okay, so being able to understand things about a signal by looking at its Fourier transform is a useful thing to be able to do. Okay. Okay, so and next question is are the Fourier transforms invertible? Okay, well, I've written down some formulas for, sorry, I apologize. I forgot the inverses here. Okay, I've written down some formulas for the inverses. Okay, there's 4 of them. Okay, but I've done it just by kind of bogus crossing my fingers. All right, so first you should show really that the transforms are in fact invertible. And then if you've shown that, are our formulae for the inverses correct? Okay. We're going to see that the answer is no. Okay, in general, and there's substantial reasons for that. Okay, and reasons typically will have to do, as we'll see, with the rather poor performance of the Dirichlet kernel that we have seen when we talked about convolution. The poor performance of the Dirichlet kernel as an approximate identity. It's not an approximate identity, and that causes all manner of problems with the formulae actually giving you the inverse of the transform. And so we'll talk about all of those things. Okay. All right, so that's our introduction to Fourier theory. And what we'll do is next time we'll start talking carefully about the CDFT. Okay, and looking at some of its properties.